Right folks, here is the summary or walkthrough, whatever you want to call it, for the organic nomenclature activity I gave you today. First question was to explain what is meant by the term structural isomers. It's a very important definition that you need to get correct. It is molecules with the same molecular formula but different structural formula. So they've got the same molecular formula, like C3H8O, for example, but different structural formula. So CH3, CH2, CHO versus CH3, CO, CH3, as an example. So that was the essence of the first one, structural isomers, not to be confused with stereoisomers. So stereoisomers have the same structural formula, but a different arrangement of atoms in space. You need to make sure you've got both those definitions locked down. And then you're asked to draw in different guises, different structural isomers for pent-2ene. And there are three types of structural isomer. There are functional group, chain, and position. We'll start with functional group, and pent-2ene is C5H10. So how are we going to rearrange those atoms so we end up with a different functional group? And hopefully you remember the easiest thing to do with any alkene to turn it into a different homologous series with a different functional group is to ring it. So I'm going to put all 5 carbons in a ring, and we'll call that cyclopentane. There are other options available. You could have had methyl cyclobutane, you could have had 1,1-dimethyl cyclopropane or 1,2-dimethyl cyclopropane, but as long as it satisfies the laws of bonding. So both of these things must be C5H10, and this is definitely C5H10, but the structural formulas are in fact different. Chain isomers. So chain isomers needs to have a different chain length. So how am I going to go about doing this? Well, it's pent-2ene, so it's 1, 2, 3, 4, 5. So how am I going to go? I've got 5 carbons in the chain. I need a shorter chain. So I'm going to start with 4. Okay, and the key thing is keep the double bond in the same position, because you don't want to make it a position and a chain isomer at the same time. So I'm going to keep the double bond there. So it's but-2ene. And then I've just got that extra carbon to put as a methyl group. And there's only really one place I can put it, or 2 places, either there or there, but both would give me the same molecule. So I'm going to put it there, and then I'll start numbering from here. 1, 2, 3, 4. So that becomes 2-methyl but-2ene. And again, I'm pretty sure, and you can confirm this, I don't need that 2. I've just called it methyl but-2ene. That is absolutely fine. And position isomer, so that just means I need to put the position of the functional group in a different part of the molecule. So alkene's fairly obvious. Currently it's on the 2nd carbon, so if I simply move it to the 1st carbon, I'll end up with pent-1ene. Okay, so that was that first activity. On the second part of this video, I'm going to go through the free radical substitution part. Okay, so I'm just going to clear the boards and then we'll go through that. Okay, folks, we're on to the second part now, which is free radical substitution. The first question was to write an equation for the initiation step for the reaction between ethane plus chlorine. So the initiation, hopefully you know by now, your halogen with the presence of ultraviolet light becomes 2 chlorine radicals. Yeah, and I'll just put the answer to question 2 whilst we're here. What is the UV light for? What actually happens? What are you doing to this chlorine molecule, which is that, to end up with 2 lots of those? Hopefully you can see on that diagram, I'm actually breaking the bond, and breaking bond is very much an endothermic process, so energy needs to be provided for it. So all that's happening is that it is providing energy. So the ultraviolet light is providing energy to break covalent bond. And then we've got 2 different equations to write. So question 3a and 3b. So 3a and 3b. 3a says that write a balanced equation of the reaction of chlorine with ethane to make chloroethane. So ethane, CH3, CH3. Again, use structural formula when you're writing equations. You could put C2H6 for this particular alkane because there's nothing else it could be, but again, you'll get penalised if you start putting it for molecules where you do need to actually show the structural formula. So I just say do it all the time. Apart from glucose you can just put C6H12O6 because scientists around the world recognise that that is actually glucose. And we're reacting with chlorine, and it's making chloroethane. And then it's not quite balanced because I think there's another product we need to do here. Don't forget, it's free radical substitution. Substitution means we are swapping something. So clearly you can see what I'm doing is I'm swapping one of those hydrogens for a chlorine, all right, to end up with this thing over here. So how do I go about, so that just means that there must be another product formed. Well, where does that hydrogen go? It bonds with the other chlorine that's not currently accounted for. So again, you always end up with a hydrogen halide as your product. So in this case, we get hydrogen chloride. And the second one, we're taking ethane plus chlorine. So it's the same thing. And this time we're making 1,1-dichloroethane. So, and I know I'm going to get that produced as well. But then balancing this, what's the difference between these two equations? Well, here I'm swapping one hydrogen for a chlorine. Whereas here, the bottom one, I've got a CH3 there, I've only got a CH, and I've got two Cl. So I'm swapping two hydrogens for two chlorines, which means that I'm going to need two lots of chlorine molecules. And as a result of that, I'm going to end up with two lots of hydrogen chloride produced. Okay, so looking at the rest of this particular activity, so question 4 and 5 next. Question 4, one of the products from this reaction is chloroethane. Write a propagation steps to form chloroethane from chlorine. So again, we're going to be taking this reaction here and we're going to be writing the propagation steps. So what I'll do is I'll just get rid of that and that. And I'll write the propagation steps for question 4 above it. Okay, so what always happens, you've got two propagation steps, and in the first propagation step, first thing that always happens is you get hydrogen theft. So we'll take our ethane and we're going to take our chlorine radical, and the chlorine radical is going to steal one of the hydrogens from the ethane. Now it doesn't really matter which hydrogen we steal here because they're all in the same environment. So I'm just going to take CH3, CH2 radical and HCl. So always in the first propagation step, you make your byproduct, your hydrogen halide. Second propagation step, now we will take the CH3, CH2 radical. You'll notice I've got the radical just on the end of the chain, which is absolutely fine. If you want to be more precise, you can put that radical actually on top of the carbon. But don't put it at this end because that will just show that it's in the wrong place. And it reacts with more chlorine to make CH3, CH2, Cl, and then regenerate the chlorine radical. And that chlorine radical can then go and do propagation step 1 all over again. Yeah. So how do we know they're propagation steps? Well, number of radicals basically on either side of the equation. With the initiation step which had earlier, 0 radicals became 2 radicals. Propagation steps, 1 radical on either side. Yeah. And termination steps is when any 2 radicals combine to become 0 radicals. So, question 5, again, we're looking at the second reaction we had there, so it would have been this one. Okay. So let's write the 2 propagation steps for this particular reaction just here. Okay. Okay. It's 1,2-dichloroethane can be formed. One of the products is 1,1-dichloroethane. Write a pair of propagation steps to form from dichloroethane from chloroethane. So we're starting this time with that. Okay. We'll take our chlorine radical. It'll do exactly the same thing. We've got to be careful now though, because it does tell us in this question, I'm just going to get rid of this equation for a moment, that we're going to be forming dichloroethane. All right, so we're going to be forming 1,1-dichloroethane. So we're going to end up with the chlorines on the same carbon. So when I take a hydrogen this time, I could take that hydrogen or I could take that hydrogen, but to make sure that I end up with 1,1-dichloroethane, I'm going to have to make sure I take the correct one. So it'll look like very good. And then this radical here can react with more chlorine to make and regenerate the chlorine radical. So I've ended up with 1,1-dichloroethane there, which is what was asked of me. Okay, so question 6 and 7. What would the product be of ethane with a large excess of chlorine? So again, let's go back to the equation. So the original equation was ethane plus chlorine makes CH3, CH2Cl, and HCl. But obviously this is not the best way of making halogen alkanes because you end up with a mixture of products. As long as there is still hydrogens on my product, their hydrogen theft or propagation, step 1, can still take place. So how do we go about ensuring, what would happen if we had an excess of this? Well, if you have an excess of the halogen, you end up with promoting further substitution. So you maximize further substitution, which if that is the case, we will swap all of the hydrogens, all right, in our molecule for chlorines. So we'll end up with CCl3, CCl3, or hexachloroethane. If you wanted to minimize further substitution, you'd have this in excess, and you'd end up with this as your major product. You can't eliminate further substitution, but you certainly can minimize it. And the final step was, so question 7, some 1,2-dichloroethane can be formed in a termination step. Write an equation to show how this can happen. So 1,2-dichloroethane from any of the radicals that we've seen so far. So hopefully CH. So we'll take the CH2, CH2Cl radical, react it with the chlorine radical, and end up with CH2Cl. And again, structural form is quite important here, because if you simply put this as C2H4Cl2, it doesn't tell the examiner or the person looking at it which isomer it is, and it has to be specific. It says in the question, you are making 1,2-dichloroethane. So that's the first half of today's lesson reviewed. I'll review the second half on another video.